Yeah. Okay, so we can start with the new set of instructions today, that is branch group instruction. So this is the last set of instruction in 8085. Okay, now what is branch? See, normally microprocessor is executing the program in a sequential manner. Okay, suppose we have 10 instructions, so microprocessor can start executing the program from first instruction till last instruction. Okay, that is the normal sequence. But branching means whenever microprocessor wants to jump from a particular sequence to some other location, then that is known as a branching instruction. Okay, so in short, the microprocessor executes the machine code in a sequential manner. It goes on executing from one memory location to another. Suppose we have a program that starts from memory location C000H and it goes till C009H. So microprocessor can execute the first instruction that is present at this location, then it will execute the next instruction that is present at C001H, and it goes till C009H. Okay, but the branch group of instructions are the instructions that can instruct the microprocessor to go to some different memory location. Okay, suppose here we have an instruction, we have one of the instruction that is jump instruction. Okay, so I wrote here JMPC008H. Suppose at this memory location, I wrote this instruction that is JMPC008H. So once microprocessor comes to this instruction, it will directly jump to which instruction? C008H. So it can break the sequential manner and it will directly go to C008 memory location. Okay, so that is known as a branching group instruction. So here in this case, this jump is a branching group instruction that can break the normal sequence of the program. Okay, now we have number of instructions that falls under the branch group instruction. So we can see all the instructions one by one. So first instruction we have under this group is jump instruction. Okay, first instruction is jump instruction. So students, jump instruction is again further divided into two parts. Either the jump statement is unconditional or either it is a conditional. Okay, unconditional jump statement means the microprocessor can execute the instruction without checking any of the condition. So that is known as the unconditional jump. Second one is the conditional jump. This instruction means if the condition is satisfied, only then the microprocessor will jump to the particular memory location which is given in the instruction. But if the condition is not satisfied, then it will execute the instruction which is after the jump statement. Okay, so we can start with the first instruction first. So first is the unconditional jump. Okay, so first instruction is unconditional jump. So for unconditional jump, we can write the instruction as JMP address. Okay, so this is the unconditional jump statement. So first we can see the format of the instruction. So whatever contents we have in this instruction, those contents will goes into the program counter. Okay, next after format we can see the addressing mode. So the addressing mode of these type of instructions is immediate addressing mode. Why the instruction comes under the immediate addressing mode? Because once this instruction comes within the program, then microprocessor immediately jump to this memory location. Okay, so immediately when the microprocessor jumps to this memory location, that means the addressing mode of this instruction is immediate addressing mode. Next we can see number of bytes. So this instruction will occupy how many bytes? 3 bytes of memory. Why? Because 2 bytes will be occupied by the address which is given in the instruction, because this address is 16-bit address. So in order to store the 16-bit data, 2 bytes will be required and 1 byte is used to store the opcode.
Ma'am, can you please just re-explain the intro part?
Which part?
Starting part.
Starting part where? Okay, so jump statement is the branch group statement. Jump statement is of two types. First is unconditional jump and second one is the conditional jump. Okay, unconditional jump is the statement which microprocessor can execute without checking any condition. Okay, directly when this instruction comes in the program, microprocessor will directly jump to that particular memory location which is given in the instruction. But in case of jump conditional statement, when the condition is satisfied, only then the microprocessor will jump to the memory location. If the condition is not satisfied, then it stays in the main program and it will execute the next instruction which is after jump statement. I will tell you this with the help of example. Just a minute. Number of bytes. So this instruction will occupy 3 bytes of memory. Next we can see the flags affected. So by any of the branch instruction, no flag will be affected. Why no flag will be affected? Because these branching instructions will only change the sequence of microprocessor from one memory location to another. That means only the program counter contents are changed from one memory location to another memory location. So that means for these branch group instructions, ALU is not used. Okay, we are not performing any arithmetical and the logical operations. So that means if we are not performing any ALU operation, that means flag register won't get modified. Okay, because simply we are changing the sequence of the program for execution. So that's why no flag will be affected after the execution of the jump statement. Okay, now come to the example part. So we can see the example now. Okay, so for example, we have an instruction. We are talking about the condition unconditional jump. Okay, so suppose we have an instruction JMP 2002005H. Okay, so suppose this we have an instruction in a program. So this instruction means this instruction will load the program counter with the address that is given in the instruction. So which address is given in the instruction? 2005H. So this address will be loaded into the program counter after the execution of this instruction. Okay, why? Because program counter can hold the address of the instruction which microprocessor wants to execute. Okay, so first address will be loaded in the program counter, only then the microprocessor will execute the instruction from that particular address. For example, we have a program that starts from memory location 2001H. Okay, and it goes up to 2009H. Suppose we have a program with these memory locations. Okay, now memory location 2003H, we have a instruction that is JMP 2005H. Okay, suppose at this memory location we have this instruction. So what microprocessor can do, once microprocessor okay, so program counter is initially at this memory location because program counter can hold the address of the instruction which microprocessor is executing. So currently the program counter is having contents 2003H. Once microprocessor comes to this instruction is having branch instruction. So this instruction means jump to the memory location 2005H. So once microprocessor can fetch or decode this instruction, then immediately microprocessor can jump to the memory location 2005H. But before jump into this memory location, initially microprocessor will change the contents of program counter. So after execution, what microprocessor can do? Microprocessor can change the contents of the program counter to 2005H, and after changing the contents in the program counter, then immediately it will jump to the memory location 2005H. Okay, so this is known as the unconditional jump, means microprocessor can jump to any of the location which is specified in the instruction without checking any condition. So here in this case no condition is written. Okay, so that means directly once this instruction is encountered by the program, it can directly goes into the memory location 2005H. Is it clear?
Yes, ma'am.
Okay. So next instruction we have is a conditional jump statement. So conditional jump statement means the jump statement which can be executed by the microprocessor when the condition is satisfied. So we can see the format of this instruction first. So the format of this instruction is same. The address goes into the program counter. Okay, once the instruction is executed. Now addressing mode. Again, the addressing mode is immediate because once this type of instruction encountered to the microprocessor, it will directly jump to the address which is given in the instruction. Here we have a condition. Okay, we are not writing here JMP. Here we are writing J condition. So that condition I will tell you in the tabular form. Okay, so if the condition is satisfied, then it will jump to the address which is given in the instruction. If the address is not satisfied, then it will stay in the main program only. Okay, so number of bytes. So again, this instruction will occupy 3 bytes of memory, 2 bytes for this address and 1 byte for this opcode. Okay, next, flags affected. So again, this instruction is a branch group instruction, means microprocessor can only jump from one location to another location. So no flag will be affected by the execution of this instruction. Okay, next we can see the table first. Okay. So in case of a jump statement, we have number of conditions. First condition we have is JZ. So JZ means jump if 0. So this is the first conditional jump statement. So microprocessor will jump to the memory location if in a flag register 0 flag is having 1 value. Okay, jump if 0. If the result is 0, only then it will jump to the address which is given after this condition. Okay, and if the 0 flag is having non-zero value, that means it will sorry, if the 0 flag is having 0 value, that means it will stay in the main program only. Okay, that means if the result is 0, then this condition will be executed. If the result is non-zero, that means this instruction will not be executed or will be ignored by the microprocessor. So jump if 0, that means 0 flag is having value what? 1. When the result is 0, that means 0 flag is always equal to 1. So this condition will work when 0 flag is having 1 value. Okay. Next condition we have is JNZ. This instruction means jump if no 0. This instruction means it will jump to the address which is given in the instruction when 0 flag is having 0 value. So when the result is non-zero, then this instruction will be executed. And when the result is non-zero, that means 0 flag is having 0 value. Okay. Next condition we have is JP. This instruction means jump if positive. Jump if positive means when the result is positive. So how we will come to know whether the result is positive or not? When in the accumulator, that we already did in the flag register, when in the accumulator most significant bit is equal to 0, that means number is positive. When in the result most significant bit is equal to 1, that means number is negative. Okay, so that means these two values depends upon the value of sign flag. When MSB is equal to 0, that means sign flag is equal to 0 and the number is positive. Okay, so how we will come to know that whether the number is positive or not? With the help of sign flag value. So when the sign flag is having 0 value, that means number is positive. So this condition will work when the number is positive by checking the contents in the sign flag. Okay, next is jump if minus. So jump if minus, this instruction means when the sign flag is having 1 value, then it will jump to the particular memory location, and it is having 0 value, then it will not go to the memory location that is specified in the instruction. Next is JPO. JPO means jump if parity is odd. Jump if parity is odd. Okay, so this means microprocessor can jump to the address which is given after this condition if the parity is odd. And when in a result parity is odd, that means we can reset or set the value of parity flag. We can reset the value of parity flag. So when PF is equal to 0, then it will jump to the address. Otherwise, it will execute the next instruction which is after this. Next we have is JPE. This instruction means jump if parity is even. Jump if parity is even. So when the parity is even, that means parity flag is equal to one value. Okay. Then after JPE, next we have is JC. JC means jump if carry. So if in a result carry is generated, that means carry flag is having what value? Carry flag is having one value. So this condition or the microprocessor can jump to the particular address when in the carry flag value is 1. If in the carry flag value is 0, that means it will not jump to the address which is given after this condition. Okay. Next we have is jump no carry. This instruction means it will only jump to the address when no carry is there in the flag register. So when CF is equal to 0, then it will jump to the particular location. Otherwise, it will stay in the main program. So see, we have these 8 jump conditions in 8085. So any of the 8 jump conditions we can use in a program while we are writing the program. So basically these instructions are used in a program. Okay, so these are very, very important that we can see how we can apply these instructions in a program. Okay, so this is about the jump condition address. So here, for example, we have a instruction. Initially, I am assigning D register with value, suppose D, 05H. So after this, I am writing DCRD. Okay. Then I am writing the condition jump no 0 to up. And here I am writing some instructions. Suppose move A, M. And up we have here. Okay. Just a minute. Just a minute. See. So suppose we have a program MVI D, 05H, then I am writing this instruction, that is move A, M. एक मिनट अच्छे से लिखती हूँ. Up, and here I am writing move A, M. Then here I am writing DCRD, and then again I am writing here J and Z up. Okay, so here you can see in this example we have a conditional jump statement. Okay. So suppose this is a memory location C001H. This is memory location 002. This is memory location 3, and this is memory location 4. Okay. So here we are denoting the address with this with this word that is up. Okay. So this instruction means initially we can assign 05 to this D register. Okay, so by this instruction D is having 05 value. Okay, next we can assign whatever address we have in the memory location that is pointed by HL pair into A register. So these instructions we did in the data transfer group. Okay, so after transferring the data of the memory location into the accumulator, now we are going to decrement the contents of D. So initially D is having value 05. After the execution of this instruction, D is having value 04 because DCR can decrement the register value by 1. Okay. Now, after this instruction is written, that is branch instruction. This is jump no 0 to up. So this instruction will check the contents of the register which is above it. So this register is having value now 04. So 04, if it is having value, that means it will jump to the memory location that is up. Okay, and up में कौन सा memory location है? C002H. So this instruction will jump the microprocessor to the memory location C002H, because this instruction will be executed if the result is non-zero. So here D is having 04 value. That means the value of D is non-zero. So this instruction will work when this is having non-zero value, and it goes to the address which is pointed by this word, that is UP, that is up. Anything you can write here. Okay, so this is about the jump conditional statement. And if I am writing here JZ, so this instruction will only work when D is having value 0. When D is having value 4, 5, 3 and 2 and 1, then this instruction won't go to up. Okay, because D is having non-zero value. So this instruction will not work for non-zero value. Okay, so it will not go up to up. When D is having 0 value, only then microprocessor will jump to the memory location that is C002H. Okay, we can do the program and then you will get the better idea about the conditional statements. Okay, so is it clear to all of you? Is it clear? Sakshi, Nicholas?
ma'am.
Arsh? Arsh?
Yes, ma'am.
Chalo. Next instructions we have, that is the call instructions. Okay, so next set of instructions we have a call instructions. Again, call instructions are conditional and unconditional. So first we have a unconditional call statements, and second we have a conditional call statements. Okay, now jump statement can redirect the microprocessor from one location to the another location, but the another location where microprocessor can redirect the where microprocessor is redirecting is in the same program. Okay, means we have a program that starts from C00H and it goes up to C009. Here I am writing the instruction JMP C008H. So that means in case of jump statement, microprocessor is redirecting to the memory location which also belongs to the same program. Okay, because one program can occupy these memory locations that start from this to this. Okay, so it will redirect to the memory location which is also the part of this program. This is in case of the jump statement. Okay, but in case of call statement there is a difference. Okay, in case of call statement, microprocessor is redirecting to the location which is not the part of this program. Okay, if I am writing here call and address, so I am writing here address A00AH. So that means microprocessor can redirect to the memory location which is not the part of this program, because this program can occupy only these memory locations. Okay, and A00A do not belong to this address. Okay, so in case of call statement, microprocessor can jump to some other program, and in case of the jump statement, microprocessor can jump to the particular memory location which is also the part of the main program. So this is the main difference between jump and the call statement. Okay, so in case of call statement there are two programs. Okay, one is the main program where the call statement is written, and second program where after calling microprocessor can switch. That program is known as a subroutine program or a sub program. Okay, so one we have a main program and second we have a subroutine program. Okay, and in main program call statement is written, and after execution of this call statement microprocessor can jump to the subroutine program which is not the part of the main program. Okay, so that is known as the call statement. Now we can see how call statement will work. Okay, so suppose we have a program that starts from memory location C000H and it goes up to C009H. Okay. Here at this memory location, currently program counter is executing the instruction which is present at this memory location. So here, suppose we have a unconditional statement, we can write like this. Okay. Call address. So here we have a call instruction. So see, this is a 3-byte instruction. Okay. So if we want to store the 3-byte instruction in a memory, then how many memory addresses are required? 3 addresses, because each address can store only 1 byte of data. Okay. So each address can store only 1 byte of data, and this instruction is of 3 bytes. So that means this instruction is stored in 3 consecutive memory locations in the memory. Okay. So initially in the memory, opcode is always saved. So at this location, there is a opcode of call instruction is stored. At the next memory location, lower order byte of the address is stored. Okay, so here lower order byte of the address is stored, and at the next memory location, higher order byte of the address is stored. Okay, so this is how 3-byte instructions will be stored in the memory. Okay, this we can see again in the programming part in detail. Okay, so suppose currently program counter is at this memory location, and here we have a call instruction. Okay, so once this instruction will be fetched by the microprocessor, after fetching it will decode this instruction, and after decoding it will execute this instruction. So this instruction means microprocessor can jump to the memory location which is specified here. So suppose in this we have an example that is called A009H. Okay, so suppose we have this example. So this instruction means lower order byte, that is 09, is stored here, and higher order byte is stored at this memory location. So once this instruction is executed by the microprocessor, what microprocessor can do? Microprocessor can push the contents of the program counter into the stack memory. Why? Because after executing the subroutine program, now again microprocessor will get back to the main program. Okay, so from this location, microprocessor jump to the subroutine program, and after completing the subroutine program, again the microprocessor will get back to the main program. Okay, so this is how call statement will work. That means this instruction is used to transfer the program control to the subroutine program. Okay, so whenever this instruction is executed by the microprocessor, so the program control is transferred from the main program to the calling program, or we can say from the main program to the subroutine program. Okay, now, so when the microprocessor can jump to the subroutine program, at the same time the current status or the current contents of the program counter will be pushed on the stack. Current contents of the program counter will be pushed into the stack. So that means the address of the next instruction will be pushed on the stack. So after executing this instruction, microprocessor will go to the subroutine program, and after completing the sub program, it will come again to the main program. Okay, and here now at which location microprocessor will come? To the next memory location, that is C004H. So here we have a program counter is having value C004H, because when the microprocessor is executing any instruction, at the same time program counter is loaded with the address of the next instruction. Means parallelly or side by side, two things will be going on in the microprocessor. Okay, once first instruction is fetched and decoded by the microprocessor. Okay, and when the instruction goes for the execution in the microprocessor, at the same time the program counter is uploaded, or program counter is loaded with the contents of the next instruction. Okay, means we have two instructions, like we have first instruction at this location and second instruction is at this location. Okay, so the instruction of this address will be fetched, it will be loaded, sorry, it will be fetched, it will be decoded by the microprocessor. Then after that, this memory location is not required by the microprocessor, because now only execution part is left. So when the microprocessor is executing the instruction which is inside this memory location, at the same time program counter will change the contents from this memory location to this memory location. Okay, so when this instruction is being executed by the microprocessor, at the same time program counter will be changed to this new address, that is C004H. So before jumping into the subroutine program, this address will be stored in the stack memory. Okay, so this address will be pushed on the stack memory. When we want to add something on the stack memory, then we can say it is a push operation. And when we want to read something from the stack memory, then we can say that operation is a pop operation. Okay, so in this calling operation, we can push the contents of program counter into the stack memory. So that means we are using the push operation. Okay, so after this, after pushing the contents of the program counter, the stack memory or the stack pointer will be decremented by 2, because after push operation in case of stack memory, always the address of the stack pointer is decremented by 2. That we did in the stack instructions already. Okay, and when we can perform the pop operation, then the stack pointer is incremented by 2, and when we can do the push operation, then the stack pointer is decremented by 2. Okay, so after the execution of the subroutine program, once the execution of the subroutine program is done, okay, then it is essential to transfer the program control back to the main program. Okay, so how the microprocessor can come to the main program? By checking the contents of the program counter in the stack memory. Okay, so program counter come here, or microprocessor check the contents of the program counter here, and after popping the contents from this stack memory, it will get back to the main program. Okay, so this is how call instruction will work. Now see. So the format of this instruction is after call operation, what we can do, we can push the contents of the program counter into the stack memory. Okay, so we can see the format of the instruction. So the higher order byte of the program counter, program counter contains the 16-bit data. So higher byte will be stored at one memory location and lower byte will be stored at another memory location. Okay, so higher order byte of program counter is stored at SP-1, and the lower order byte of the program counter is stored at SP-2. Okay, and after pushing the contents of the program counter, then the stack pointer is decremented by 2. So now the stack pointer is having value SP-2. Okay, and then program counter is loaded with the new address, which is the starting address of the subroutine program. Okay, so this is the format of this instruction. Now we can see the addressing mode. So the call instruction comes under two addressing mode. First one is the immediate addressing mode, and second one is the register indirect addressing mode. Why this call instruction falls under two addressing mode? Because immediate means once this instruction is encountered in the program by the microprocessor, immediately microprocessor can jump to the memory location which is specified in the instruction. So that means immediate addressing mode. Now why it is known as a register indirect mode? Because side by side whatever contents we have in the program counter, that we can push into the memory location, and that memory location is specified by the stack pointer. If in a program memory location where we want to push the contents is specified, then we can call that instruction as a direct. But in case of call instruction where we have to push the contents of the program counter is not specified, that means that is specified by the stack pointer. Okay, so that means That means the addressing mode is register indirect, means call instruction push the contents of the program counter into the memory location that is specified by the stack pointer. So the process is indirect. So that's why the addressing mode is register indirect addressing mode. Next is the flags affected. So after the execution of call instruction, no flag will be affected, because again this is the branch instruction which can redirect the microprocessor from one location to another location. Next we have is the number of bytes. So this instruction will occupy 3 bytes of memory. 2 bytes is for address and 1 byte is for opcode. Okay, so total this instruction can occupy 3 bytes of memory. Now we can see the example. So again I will give you one more example. Suppose we have an instruction call D015H. Okay, so suppose we have this instruction and we have two programs. One is a calling program, or that we can call as a main program. Okay, that starts from memory location C00H to C009H. Okay, another program we have a subroutine program. Okay, and subroutine program starts from memory location D015H. Okay, so here we have one program and here we have second program. Now, suppose at this location we have C001H, we have an instruction called D015H. Okay. Now, and this instruction will occupy how many bytes? 3 bytes. 1 byte for the opcode of call and 2 bytes for D015H. So after this, next instruction will be at memory location 1, 2, 3 will be used by this. So next instruction will be at memory location C004H. Now, how this instruction will work? See, microprocessor currently program counter is having address C001H, and at this address we have an instruction that is called D015H. So what microprocessor can do? Microprocessor can jump to the memory location D015H where subroutine program is written. But before jumping into this location, microprocessor will push the contents of the program counter into the stack memory. Okay, so when this instruction is being executed by the microprocessor, at the same time program counter is loaded with the address of the next instruction. So next instruction is at address C004H. So these contents of the program counter will be loaded into the stack memory. So suppose here we have a stack memory. Okay, and stack currently stack pointer is at location this, and this location is suppose A00AH. Okay, so this is the current location where stack pointer is there. So when the higher order byte is pushed, where higher order byte of the program in SP-1. So SP-1 location is this, that is A009H. So at this location, higher order byte of the program counter is stored. So out of C004, which one is the higher order byte? C0. So C0 is stored here, and the lower order byte of the program counter is stored in SP-2. So at SP-2, which value is stored? 04 will be stored. And after pushing these contents into the stack memory, stack pointer is decremented by 2. So before execution, stack pointer was A00AH. After execution, now the stack pointer points to memory location A008H. So after execution, stack pointer is having value A008H. Okay. So that means this is the register indirect way, because the contents of the program counter will be pushed into the memory location, that memory location which is specified by this stack pointer. Okay, and stack pointer specified to which memory location? A00AH. Okay, now after pushing the contents of the program counter into this memory location, now the microprocessor can jump to this location. But now microprocessor can execute the instruction which is present here, but before executing the instruction, microprocessor can execute only that instruction whose address is in the program counter. So the program counter previous contents are stored in the stack memory. So now the program counter is updated with the new address, and that address is D015H. So that means after pushing the contents into the stack memory, now the new address which is given in the instruction will be loaded in the program counter. So now the program counter after the execution which is having new contents, that is D015H. Now the microprocessor can start executing the instructions of this program that is written in the subroutine part. Okay, so this is about the unconditional call statement. Is it clear?
Yes, ma'am.
Okay, so next, तो ये तो था unconditional. Now we can see the conditional call statement. So in case of conditional call statement, everything is same, but microprocessor can jump to the subroutine program if condition is satisfied. Only this is the difference. Okay, other processes same. बाकी सब process जो है वो normal unconditional जैसा ही है, but in case of the conditional statement, microprocessor can jump to the subroutine program if the condition is satisfied. If the condition is not satisfied, then microprocessor can execute the instruction which is written after the call statement in the main program. Okay, so again here we have call condition address. Okay, so here condition is written. Again, higher order byte will be pushed in SP-1, lower order byte will be pushed in SP-2, and the stack pointer is decremented by 2. Okay, after this, program counter is updated with the address or the starting address of the subroutine program. Addressing mode is again immediate and register indirect addressing mode. No flags will be affected and number of bytes are 3 bytes. Now in this case, we can see the different types of conditions. So first condition is CZ. So this instruction means call if 0. These all conditions are like the jump statement only, but in case of J we can write C. So this instruction will execute if in a flag register 0 flag is having value 1. So if the 0 flag is having 1 value, then the microprocessor can execute the instruction and jump to the subroutine program that starts from the memory address which is given after the condition. Okay, and if the 0 flag is having 0 value, then it will do nothing. It will execute the instruction which is written after this instruction in the main program. Okay, rest everything is same. So here call no 0. So this instruction will execute if in a 0 flag we have a 0 value. Okay, next CP. So call if positive. So if the result is positive, then this instruction will be executed, otherwise not. Okay, call if minus. So if sign flag is having 1 value, then it will jump to the subroutine program, otherwise it will stay in the main program. Next one is the CPO. Again same. Next is CPE, then call if carry, then call if no carry. Okay, so rest all the statements are same, only the in case of jump we can replace it with the call statement. In case of jump, microprocessor can jump to the memory location which is also the part of a main program, but in call statement microprocessor can jump to the memory location which is not the part of the main program, which is the subroutine or a sub program. Okay, so this is about the conditional call statement, and we can see one example. That is, we can write here CZ A009H. Okay, so that means if 0 flag is having 1 value, then it will call to the memory location that starts, it will jump to the subroutine program that starts from memory location A009. If 0 flag is having 0 value, then it will stay in the main program and it will execute the instruction which is written after it. Okay, and at the same time, whatever will be the contents of the program counter, that will be pushed in the stack memory, and the program counter is updated with the address which is given here. That means after the execution, program counter is having address A009H. Okay, so this is about the call statement. Okay, so next statement now we can see that is a return statement. That is RET. Okay, so this is the third type of statement, that is return statement. So return statement is also of two types, that is the conditional return statement and the unconditional return statement. Okay, now what is return statement? Return statement is the statement which is written in the subroutine program. Okay, and this return statement will work with the call statement. What call statement can do? Call statement can jump from the main program to the subroutine program. But if microprocessor wants to come back to the main program, then it will come back to the main program once this instruction will be encountered in the subroutine program. Once microprocessor can get this instruction in a program, then it will come to the stack memory to get the address of the program counter. Then after getting the address of the program counter, it will go back to the main program. Okay, so this instruction will work with the help of call statement. So we can see when this instruction is executed, the program counter is transferred from the subroutine program to the main program. Okay, that means during the call operation from the main program, microprocessor can jump to the subroutine program. Okay, and in this subroutine program, we have a instruction at the last, that is return statement. So once this instruction will be encountered or will be executed by the microprocessor, it will get back from the subroutine to the main program. But before this, it will come to the stack memory. Here it will pop out the contents of the program counter, then it will jump to the memory location in the main program. Okay, so call will move from main program to subroutine, and return will come back from the subroutine program to the main program. Okay, so this instruction means when this instruction is executed, the program counter is transferred from the subroutine to the calling program. Okay, or we can say from the subroutine program to the main program. Okay, the return address is popped out, or it is taken out from the stack memory. That means the contents of the return address will be popped out from the stack memory. That is, we can say the return address, or we can say the address of the program counter, or the value of the program counter. Okay, thus the program counter is transferred to the next instruction after the call in the main program, because call instruction is already executed by the microprocessor. Then after the return statement, it will get back to the memory location, or it will get back to the next instruction which is after the calling statement. Okay, so that is the meaning of return statement. So in case of return statement, the value of the program counter is popped out. So the value of the stack pointer will be popped out, and it will go to the lower order byte of program counter, and the value of SP plus 1 will be popped out from the stack memory, and it will be stored in the higher order byte of the program counter. Okay, and after popping the contents, then the stack pointer will be incremented by 2, because during the push operation, stack pointer is decremented, and during the pop operation, stack pointer is incremented by 2. Okay, then after this, what will happen? After this, now the program counter will be updated with the address which was in the stack memory. Okay, so this is about the return statement. Now we can see the addressing mode. So in case of return statement, addressing mode is register indirect addressing mode. So the addressing mode of this instruction is register indirect addressing mode, because indirectly whatever contents we have in the memory that is pointed by the stack pointer will be pushed into, will be popped out, and it will go into the program counter. Okay, so the addressing mode is register indirect addressing mode. Now next we have is, see, conditional statement we can write, unconditional we can write as RET. Okay, next we have number of bytes. So this instruction will occupy only 1 byte of memory, because this is the opcode only, and opcode can occupy 1 byte of memory. Next we have the flags affected. So again, this is the branching instruction, so no flag will be affected, because it will only redirect the microprocessor from the subroutine program to the main program. So no flag will be affected after the execution of the instruction. Okay, so this is the meaning of the instruction. Now again we can see one more example, that is the combination of call statement and the return statement. Okay, so suppose again our program starts from memory location A001H to A00BH. Okay, so these are the memory locations which is occupied by a program counter, and at this initially program counter is at location A001H, and here we have an instruction that is called we have an instruction called C009H. Okay, so this instruction we have. So this instruction can occupy how many addresses? 3 addresses. So at A002, we have a lower order byte 09, and at A003H, we have higher order byte, that is C0H. Okay, now once the microprocessor comes to this memory location, this instruction is written here. So initially microprocessor can fetch this instruction, then it will decode this instruction, and after decoding, at the same time program counter will be updated with the address of next instruction. So next instruction is present at address A004H. Suppose here we have an instruction move A comma B. Okay, so once this instruction is being executed by the program counter, at the same time program counter is updated with the address of the next instruction, that is A004H. Okay, and this address will be pushed by the microprocessor into the stack memory. So here in this example, this is the stack memory which starts from memory location 2FFF. So stack pointer currently points to memory location this. Okay, so initially the higher order byte will be pushed, and after pushing the higher order byte, lower order byte will be pushed. So the A0 then 04. So this is SP minus 1 and this is SP minus 2. So this is 2FFDH and this is 2FFEH. Okay, so after pushing the contents, now the stack pointer is having new address, that is 2FFDH. So this is the part of calling statement, because in case of calling statement we can push the contents of the next instruction in we can push the contents of the memory location of the next instruction into the stack memory, and once the pushing is done, then microprocessor will jump to the memory location. Which memory location? To the memory location whose address is C009H. So here we have a subroutine program that starts from memory location C009H. So now the program counter is updated with the address C009H. Okay, and this subroutine program can occupy these much locations. That is, the subroutine program starts from this location C009 and it goes up to C00D. Now suppose at this location we have an instruction RET. Okay, so once this instruction is fetched and decoded and executed by the microprocessor, what microprocessor can do? Microprocessor can jump to the stack memory. Okay, then from the stack memory, microprocessor can read the content. So it will read 04 and it will read A0. And after reading these contents and pushing these contents or adding or loading these contents into the program counter, it will come to the memory location. So after copying these contents, it will be A004H. Okay, so after popping these contents, microprocessor will jump to this memory location, and this memory location is a part of a main program. So after this, again the microprocessor can get back to the memory location A004 and start executing the program from this location. Okay, so this is about the return statement. Means during call, push operation is performed, and during return, pop operation is performed, and call will be executed with the help of return statement. Return statement alone will not work, it will work with call statement. Okay, is it clear? Yes or no? Nicholas, is it clear to you?
Yes, ma'am.
Okay. Now see, this is the unconditional statement. Now we have a conditional return statement. So in case of conditional return statement, we can write it like R, then we can write here condition. Okay. So again, the format of the instruction is same, because again, there is a little bit difference between the unconditional and the conditional. It will work without checking any condition, and it will return back to the main program from the subroutine program without checking any condition. But in case of the conditional statement, if the condition is satisfied, only then the microprocessor will get back from the subroutine to the calling program. Otherwise, it will stay in the subroutine program. Okay, so the format is same, because again return statement can pop out the contents from the stack memory. Addressing mode is again register indirect, number of bytes are same, flags affected are same, example is also same. Here instead of RET we are writing the R condition. Okay, and rest everything is same, means process is same. So here in case of conditional statements, again we have the 8 different conditions. So here we have
Ma'am.
So here we have return if zero.
Hello?
What? Yes,
हेलो मैम
बोलो.
मैम सुनो ना अभी आपके क्लास में 7 बच्चे प्रेजेंट है
अभी मत बोलो, 1 मिनट, मेरे को लेक्चर लेने दो, बाद में बात करो. See, first
नहीं
we
मैम
have
उसकी प्रेजेंट लगाओ एब्सेंट लगाओ
return if zero. So it will return back to the main program if in a zero flag we have 1 value, and if in a zero flag we have 0 value, then it will stay in the subroutine program only. Okay, next condition we have is RNZ. So that means return if no zero, otherwise so if in a zero flag 0 value is there, then it will execute this instruction and come back to the main program, otherwise it will not. Okay, next return if positive. So if most significant bit is equal to 0, then this instruction will execute, otherwise not. Next is RM. Next is RPO, then RPE, then RC, and last one is RNC. So all these instructions are same. Previous one will work when we have a call statement, and this will work when we have a return statement. Okay, शीतल मैसेज में टाइप करो क्या हुआ. Okay, so this is about the return statement. Okay, next we can see next type of instruction we have is the restart instruction. Okay, next type of instructions are restart instructions. That will be denoted by RSTN, and N is having range from 0 to 7. Okay. Okay, restart RSTN, and N is 0 to 7. Okay, Sheetal, okay. मैंने पढ़ लिया message. So restart is RSTN, and N stands for N is 0 to 7. So the range of N is 0 to 7. Okay. So see here, in case of restart statement, see in 8085 we have 2 different types of interrupts. Okay. First one is a hardware interrupt and second one is a software interrupt. Okay. In case of the software interrupts, we have 8 different types of interrupt that start from RST0 to RST7. So these 8 interrupts are the restart interrupts. Okay, that is RST and means 0, RST1, RST2 and up to RST7. So here this instruction belongs to the software interrupts, means the interrupts which are itself present in the program. Okay. So we can see, so first we can see the format of the restart instruction. So restart statement is similar to the call instruction only, but the main difference between restart and the call that I will explain you after explaining the restart statement. Okay, so the format again of the format of call statement and the return statement is same. Restart also push the contents of the program counter into the stack memory. So pushing the contents means higher order byte of the program counter goes into SP-1 and lower order byte of program counter goes into SP-2. And after pushing the contents into the stack memory, stack pointer will be decremented by 2. That is SP is equal to SP-2. And the program counter is loaded with the address which is given in the instruction. So for RST0 to RST7, we can calculate the vector address. So again, that we did in the first chapter, how we can calculate the vector address. So after the execution of this instruction, program counter is loaded with the vector address of that particular instruction. So here, program counter is having value n into 8 in hexadecimal. Okay, that I will tell you. See, so the after the execution, the program counter is having value n into 8 into hexadecimal. Now we can see the after this we can see number of bytes. So this instruction will occupy only 1 byte of memory, because in this instruction no address is explicitly specified. Okay, so this instruction is having only opcode, so that's why this instruction will occupy 1 byte of memory. Next one we have is the flags affected. So this instruction will not affect any flag again, because this instruction can only jump to the subroutine program whose address is given in the instruction, and that address will be calculated by multiplying the number by 8 in the hexadecimal form. Okay, so no flag will be affected. Now see, we have RST0, then we have RST1, RST2, RST3, 4, 5, 6 and 7. Now calculate the vector address for all the 8 instructions. 0 into 8 is 0000H. 1 into 8 is again 0008H. Next is 2 into 8 is 16. Okay, so 16 when we can convert in hexadecimal, then it is 0010H. Kaise? See, 16 when we can divide 16 by 16, then quotient is 1 and remainder is 0. So we can write 0, 0, then we can write quotient and then we can write remainder. So it will be 0010H. Next is 3 into 8. So that is 24. So when you can divide a 16 by 24, then it becomes what? It becomes 18. So 18H. Next we have is 4 into 8. That is 32. So that is 0020H. Next we have is 5 into 8. That is 40. So 40 is 0028H. 6 into 8 is 48. That is 0030H. And last one is 7 into 8. That is 50. And it is 0038H. So this is the vector address of RST0 to RST7. Okay. So see, this instruction will transfer the program control to the specific memory location as shown in this diagram, in this table. Okay. So when this instruction is executed, the program counter is updated with the new vector address which is given in the instruction. Suppose in a program we have a instruction RST7. So usse kya hoga? Program counter is updated with the new address, and that address is 0020H. Okay, so it is used just like a call statement only, but the only difference is call statement bhi kya karta hai? If I am writing call 0028H, so what it will do, it will push the contents where this it will push the contents of the next memory location in the stack memory, okay, using this formula. And after pushing the contents of the program counter, it will go into the subroutine program which starts from this memory location. Okay, after this the program counter is updated with 0028H. In the call statement we are doing like this. Similarly, in case of RST0, if this instruction we have, then again the microprocessor can push the contents of the instruction, push the contents of the memory location which is after this instruction into the stack memory, and after pushing the contents it will jump to the memory location which is specified by calculating the vector address. So it will go to the memory location 00008, and the program counter is updated with this address, that is 0000H. So that means call and restart statement are doing the same functionality. Then what is the difference? Why we are using the new set of instruction if we have already this instruction? Tell me why we are using this instruction if the call statement is also doing the same process that restart statement is doing. See, why we are using this statement? Because this instruction will occupy less memory as compared to call statement. If we are doing the same thing with this instruction, then this instruction will occupy how many bytes? 3 bytes. But if we are performing the same functionality with this instruction, then this instruction will occupy how many bytes? 1 byte. Okay, so that's why we are using, to save the memory space, we are using the restart statement instead of call statement. Okay, but restart statement will work for only these 8 memory locations. Okay, but call statement can do or call statement will work for number of memory locations, that is 65,536 memory locations we have in 8085. So call statement will work for all the memory locations, but this instruction will work for only these 8 memory locations. Okay, this restart statement will not work for 0028H, because for restart statement we have only 8 standard vector addresses. So for only 8 vector addresses it will work. Okay, now next thing, why I am writing here into 8? Because every two instructions is having the 8 memory locations gap. See, first location starts from 0000 to 0008. That means 8 memory locations are there in between 0 and 1. Next, after 0008, next memory location we have is 0010. Then again we have a space of 8 memory locations, because here we are not talking about the decimal values. Here we are talking about the hexadecimal. So in hexadecimal, after 0008, we have next memory location is 0009. Then we have 000A, then 000B, then C, then D, then E, then F, and after F we have 0010. So you can see we have 8 different memory locations in between 8 and 10 also. So that's why we can multiply the next n by 8, because there is a gap of 8 memory locations between each restart instruction. Okay. So this instruction means, in short, I will tell you again, this instruction will transfer the program counter to the specific memory location which is given in that diagram. Okay, it is basically used as a call statement, but the first difference is restart statement will occupy 1 byte of memory, while call statement will occupy 3 bytes of memory. And second thing is, call will jump or call will be used for all the memory locations that are in 8085, but restart statement will work for only 8 different vector addresses. Okay, then before transferring the program counter to the instruction, following the vector address, RST instruction saves the current program counter contents on the stack memory by using the push operations. Okay, these instructions can be used as a software interrupt in a program to transfer the program execution to one of the 8 locations that depends upon which RST instruction we are executing. Okay, so this is about the restart statement. So if you have any doubt, then you can ask. Any doubt? Okay, and the addressing mode of this instruction is also register indirect addressing mode. That topic is skipped. That is register indirect addressing mode. Okay, so now we are left with only one instruction, and that is a very small instruction. That is PCHL. PCHL means load the contents of the H and L register into program counter. See, in case of PCHL, we have HL pair and we have program counter. Program counter is of 16-bit. HL pair is also of 16-bit. That means 16-bit value of HL pair microprocessor can load into 16-bit program counter. Okay, so we have an instruction PCHL. This instruction means load the contents of HL into program counter, that is PC. Next we have is the format. So in case of format, the higher order byte, that is H, that will be loaded into higher order byte of program counter, and the lower order byte, that is L, will be loaded into lower order byte of program counter. Okay, next we can see the addressing mode. So here the addressing mode is register addressing mode, because after the execution of this instruction, the contents of this register pair will be loaded into program counter. Okay, so that means we are only dealing with the 2 different types of register. One is the special purpose register and the second one is the general purpose register. So this instruction means to load the contents from the general purpose register to the special purpose register. So that means the addressing mode is the register addressing mode, because both the source as well as the destination are registers only. Okay, next, after addressing mode, flags affected. So again, this is a branch instruction, so no flag will be affected after the execution of the instruction. Next is the number of bytes. So in this instruction, you can see there is no address given, no data is explicitly given. So that means this instruction will occupy only 1 byte of memory. Okay, now after this, we can see the example. So suppose we have a instruction PCHL, and in H register we have value 12 and in L register we have value 24. Okay, and before execution, program counter is having value A001H. So program counter is having value this, and H and L pair is having value 12 and 24. So after the execution, what will happen? After execution, H value will be loaded into higher order byte of program counter, and L value will be loaded into lower order byte of program counter. So after execution, PCH is having value 12H and PCL is having value 24H. So these are the values after the execution. So if we are writing it as PC, then the new value of program counter will be 1224H. Okay, so this is how this instruction will work. Means we are loading the HL pair with value first 1224H. So this instruction will load HL pair with 1224H. After this, we are writing the instruction PCHL. So this instruction will copy the contents of HL pair into program counter. So after the execution, program counter is having value 1224H. Okay, so this is the meaning of this instruction. Is it clear? Is it clear?
Yes, ma'am.
See, this instruction is again similar to the jump statement. How? Jump statement में हम क्या करते हैं? We are writing like JMP and we are writing here address. So suppose we are taking here JMP 1224H. Okay, and after the execution of this instruction, program counter points to memory location 1224H, because now the microprocessor can jump to this memory location. So when the microprocessor can jump to this memory location to execute the instruction that is present here, so what it will do, it will change the contents of the program counter to the address which is given here. So program counter is equal to 1224. So either we can write this or we can write this. Okay, but again the difference is here this instruction is of 3 bytes, 1 byte for LXI and 2 bytes for 1224, and this instruction is of 1 byte. So that means this instruction will occupy 4 bytes of memory, whereas this instruction will occupy only 3 bytes, 2 byte for this address and 1 byte for the opcode. So in a program also you can use any of the instructions, but provided some of the instructions can occupy more bytes and some instructions can use more cycle. Okay, more cycle, like we have a register indirect instruction. So for register indirect instruction, it will require more cycles to execute, but some are direct instructions, means microprocessor can take less cycles to execute the instruction. So that depends कि कितनी machine cycle कौन सी instruction को execute करने के लिए लगती हैं, and which instruction can occupy how many bytes of memory. So that depends. So you can use any of the instructions in your program, provided तुम्हें पता होना चाहिए where to use the instructions in a better way. Okay, so this is all about the branch statements. Now if you have any doubt, then you can ask, otherwise we can end the session. Is it clear to all of you?
Yes.
Okay, so in the next lecture we can start with the programming part of 8085, and also we can start with the C++ next topic, that is operator overloading.